as I went from normal to doors, the gear did come down. We did get 3 green lights, and we had a prop malfunction. At first we were confused about what had actually happened. In fact, that was our first comment, was, well, wait a second, and the captain was pretty much the same situation I was. We were both confused on what really was going on. We looked at the engine instruments. Prior to the incident, we had 100% MP on both engines and right around 35% torque. After the incident, we noticed that the left torque was up to 92% and the left prop was turning at about 55% NP.
Review of the commercial transport accident record shows inappropriate crew response to propulsion system malfunctions is a significant contributor. The number of accidents each year from this cause is not decreasing. Research also shows that pilot training in propulsion system operation and malfunction recognition is not generally available. This video has been sponsored by the FAA and CAA and created by industry leaders as part of a generic training package in turboprop malfunction recognition and response. Detailed study of the accidents suggests that turboprop failures create unusual difficulties for pilots in some situations, including identification and recognition of a propulsion system malfunction, unfamiliar sensory cues, difficulty in interpreting instrument indications, and particularly airplane control difficulties. Also, power management at low speed and low altitude is critical. Increasing power on the live engine will help climb performance, but will reduce controllability and increase thrust asymmetry. Loss of airplane control represents over 60% of all propulsion-related accidents for turboprops, and these accidents generally result in fatalities. This video will review control of the airplane with an engine out, show how to recognize an engine or propeller failure, and discuss the consequences to the airplane. The following material is not a replacement for flight manual and company procedures applicable to your aircraft type. It provides a framework within which to carry out those drills.
Initially, it was very difficult to maintain altitude. We were descending about 200 to 300 feet per minute. Our airspeed was right around 160 knots due to performing the electric override checklist for the gear. While we were running the checklist, we were able to bring the power up and we were able to get the speed up to around 180, 190 knots, which was a more normal position or normal speed for our condition. We ran the checklist. We did get somewhat normal conditions as we brought the power lever back to flight idle and back to the condition lever to feather.
Review of the propulsion-related accident record for turboprops shows that there are 2 primary situations presenting difficulty for pilots. The first situation is one in which an engine fails immediately after takeoff. In this low-speed, low-altitude configuration, it is essential to respond promptly to an engine or propeller malfunction. Failure to do so has led to loss of airplane control. First, fly the airplane. The engine itself will not fail in a dangerous manner while you take a few seconds to stabilize the flight path. It is neither necessary nor appropriate to attempt a detailed diagnosis of the failure at this time. Control the airplane using rudder to oppose yaw and keep straight, and aileron to control bank angle. Rudder input is essential to maintain control. Airspeed control is vital. Adjust the pitch attitude to achieve the engine-out safety speed V2. Initially, you will fly with wings level, steady heading, ball centered. But best controllability is obtained with approximately 5 degrees of bank into the live engine. This configuration provides optimum performance. With 5 degrees of bank applied and rudder control maintained, the slip ball will be displaced towards the good engine by about half a ball's width. Retrim the airplane in pitch to help you maintain the selected attitude, then make small adjustments. Caution! Many flight directors are not certified for single-engine operation. You may need to clear the flight directors. Consult your company procedures. Your standard operating procedures will normally include gear retraction and a check that full power is applied.
Max power. Gear up.
While transport category airplanes are capable of climb performance after single-engine failure, even during reduced power takeoffs without adding power, some airplane procedures may call for the application of full power early in the procedure. However, your first concern must be control of the airplane. Second, identify the affected engine.
It appears we've had a right engine failure.
False or misunderstood indications have led to pilots taking action on the engine when none was needed, and accidents have resulted. Dead leg, dead engine. Third, confirm the malfunction by a scan of engine instruments before deciding which engine to shut down. Do not rush. If you have auto feather, confirm it has worked. If not, the fourth action is to feather the propeller. Take a few extra seconds to be sure you are shutting down the correct engine.
Number 2 power lever. Confirm.
Slide on.
Nominate by saying left or right, or number 1, number 2, as you touch the engine control before operating it. Accidents have resulted from inadvertent shutdown of the healthy engine. Keep flying the aircraft. Don't lose the instrument scan. If control is marginal, use up to 5 degrees of bank toward the live engine. If there's a yaw when you close the throttle, restore power and check that there is really an engine failure.
That's a right engine failure.
Confirm.
Shut it down. No, that's not it. We've got adverse yaw. Bring it back up. That's just the oil content light.
Always feather the prop after throttling back to idle. This will avoid a significant drag on the airplane.
Emergency checklist.
Engine failed, fire shutdown, in-flight checklist. Power operating engine as required.
Finally, check power. Is the power setting correct on the live engine? Check drag. Is the prop feathered, gear up, flaps okay? Check trim. Are rudder and aileron forces trimmed out? Never let the airplane get slow. Thrust asymmetry and low airspeed both reduce control authority. If you can't maintain speed, you must lower the nose. Running out of rudder authority at low altitude will crash the plane. Remember, if you experience a propulsion system malfunction, control the aircraft. Identify the malfunctioning power system. Confirm the diagnosis. Feather the propeller, and then consult the checklist. The second situation, which presents difficulties for some pilots, is control of the airplane once the engine has been shut down. The pilot may have difficulty in maintaining altitude throughout the remainder of the flight, or control may be lost during final approach if airspeed drops below minimum control speed. Take time to plan the descent and approach. Maintain target airspeed at all times. Decide where flap and gear selections will be made, and check minimum engine-out approach speeds, committal height, and go-around procedure.
Decision height is 573 feet under pressure altimeter. The missed approach is climbed to 2,600 feet on a 071 degree track to the Ottawa. Any questions?
Decide how to secure the engine at this point. There is no real benefit from running an engine at idle as a source of electrical and hydraulic power. Accidents have resulted from attempted go-arounds in this configuration. If you leave the engine running at idle, you must still feather the prop. Using target power settings will reduce your workload. Carefully retrim with each change in power or speed. On final approach, trimming rudder to 0 will assist in keeping control during landing. If you have to go around, control the aircraft as you would in the after takeoff case. That is, use the flight instruments to select and hold a target pitch attitude and keep straight. Never let the airplane get below the approach speed. Low speed creates high drag and reduced control authority. Remember, adding power to increase speed will increase the control inputs you need. Be ready for a yaw towards the live engine as you close the power lever. Avoid reverse thrust.
Initially, we were confused and exactly why exactly what was going on.
We have discussed the handling of the airplane with an engine out. Now let's discuss malfunction recognition. Here are some typical malfunctions and appropriate responses for both a fixed shaft and a free power turbine configuration. Refer to your company procedures for specific details of checklists. The most typical malfunctions will be shown here. A wider range of possible problems is discussed in your text material. Some of these may be alarming, with noise, vibration, and smoke. But always fly the airplane first. Propeller blades are tested to high speeds, so extremely rapid pilot action is not needed to safeguard engine integrity. Check the value, rate of change, and change direction for each parameter. Scan all parameters. Look for patterns, change from normal values. Cross-check between engines.
Okay, it appears we've had a right engine failure.
That's confirmed. Right engine's failed.
With the engine at full power and propeller at maximum RPM, ITT, torque, propeller, and engine speed increase to the high end of the scale near redline. Fuel flow is high. Both engines look the same. At cruise power, all parameters are at lower values than takeoff, but much higher than for taxi. Again, both engines look the same. A number of accidents have involved an engine perceived to be failed or at low power during takeoff after rotation. You will now see the symptoms of a free turbine engine with low power due to a flameout or turbo machinery failure. The first symptom is likely to be the need for rudder input as the airplane begins to yaw. Engine RPM is lower than expected. ITT will change from the expected value. Torque is low. Propeller RPM could look normal. Auto feather may engage. If not, you may need to feather the prop promptly. The recommended approach is to continue the takeoff to safe maneuvering altitude. For a single shaft engine with a failure at takeoff, symptoms are very similar. RPM drops off quickly. It may fluctuate. ITT will change from the expected value. Torque and fuel flow are low. Again, it is recommended to continue the takeoff to safe maneuvering altitude. Given an engine failure after rotation during a reduced thrust takeoff, you may wish to increase power on the remaining engine. Be ready for increased thrust asymmetry if you use this strategy. If the propeller does not have auto feather or a negative torque sensing system, rapid action to feather the propeller is advised. Familiarize yourself with the required action before the emergency occurs. An engine flameout in cruise allows some more time for evaluation of the situation. You will now see a free turbine engine flaming out or shutting itself down. Once again, the first symptom may be a need for rudder input to control the thrust asymmetry. ITT and NG begin to fall. Propeller torque drops off rapidly. RPM stays constant. Fuel flow drops as the pilot throttles back. Airspeed is dropping. The crew confirms which engine is involved, feathers the prop, secures the engine, and keeps flying the airplane. For a single shaft engine, the clearest indication of engine failure is a decrease in RPM, associated with the need for rudder input as the plane yaws into the bad engine. For a free turbine engine, a propeller overspeed will be indicated by a sudden increase in propeller RPM and a decrease in torque. Other engine parameters will not change. Some variability in symptoms can be expected according to the details of the installation. The scenario shown is typical for a hydromechanically controlled propeller. The recommended response is to control the overspeed by retarding the power lever and feathering the prop. It is important to verify response to the condition lever on both engines before landing the plane. Attempts to command beta mode with a pitch lock condition have led to runway departure and accidents, since one engine is producing high forward power and one producing reverse power. Unscheduled feather during takeoff may be accompanied by an increase in torque, a drop in propeller RPM, and unusual behavior of other parameters. Do not attempt to slow the airplane in descent by moving the power lever below flight idle, unless this is specifically authorized for your airplane. Attempts to move the power lever below flight idle in descent have led to dual propeller and engine overspeed, unrecoverable and complete loss of engine power, and accidents. In conclusion, the following strategy will be successful in the vast majority of cases. Fly the airplane. Identify the engine involved. Confirm the diagnosis. And feather the propeller. And again, fly the airplane with particular attention to power, drag, and trim. Airspeed is critical. Equivalent material is also available from the FAA on turbofan malfunction recognition and response.